Hi, today Ron Minnich from Google, Francois Ozog from Linaro, and myself, Don Wei from Arm, are going to present to you Linux as firmware. For the agenda, we're going to talk about LinuxBoot, the origin of the LinuxBoot, the relationship of LinuxBoot with the open source firmware inside of the Open Compute project. We're going to talk about how you implement LinuxBoot on Arm. And then at the end, I'll be talking about the relationship between LinuxBoot and the new program called Arm System Ready. At this point, I'll hand over to Ron to talk about the origin of LinuxBoot.
Hi. LinuxBoot is actually about a 21-year-old idea. It's old enough to drink. And the basic idea is to put a Linux kernel in Flash and replace as much of the firmware as possible. Back in the day on supercomputers, we were able to replace 100% of the x86 BIOS with a Linux kernel. We did the same thing for Alpha supercomputers as well as PowerPC. In more recent years, we brought that idea back to life for UEFI environments and have deployed it on x86 and ARM systems. So we put a Linux kernel in Flash. We get rid of everything that is a binary blob as we can. We can't get rid of everything on x86. We can't always get rid of everything on ARM, but we do what we can. Why do we do this? We're trying to resolve known issues with embedded exploits and bugs. Now, you may be surprised to hear that there are exploits and bugs in firmware, but it really happens. And that's said half in jest. I'm sure most of you know there are lots of bugs in firmware. The exploits may be a bit more of a surprise. A company called TSCL analyzed 100,000 UEFI images for x86 over a period of about a year. They found 10,000 different firmware images in that 100,000. 15% of them were relatively modern. They found 90,000 executables that were flagged for interesting security properties. Interesting means an executable that could phone home, send mail, manage your PC. They found a lot of programs that are related to LoJack, for example. They found certificate-related issues. They found embedded private keys. They found certificates with the string "do not trust" or that were marked as test. And this is really the tip of the iceberg. Really going through everything they found would probably take a day, but it was enough to be very, very concerning. So that's an exploit that is sort of intentional. The bugs are unintentional. We would call it a self-owned exploit, a mistake. So there is a web server and the management engine on about 1 billion Intel motherboards that would take an administration password that was 0 bytes long. How could that happen? If you have a good password and you're trying to compare it to a bad password, you might use the string of code here, the strcomp, comparing the good password to the bad password. The only problem with this compare is that it will always pass if the bad password is 0 bytes long. This is a classic mistake. I'm sure I've made it. Lots of people make it. Over a 7-year period, however, 1 billion systems or so shipped with this vulnerability. This is a tough thing to remediate. Many of those systems may still be in use. An official from the German government told me that they found it easier to shred the systems containing this vulnerability than to try and remediate the problem. Here is what a typical UEFI image looks like today. This is the reference model. The gray box on the left are things we can't possibly change. Usually on x86, that's never going to change. On ARM, we do have the option where we might be able to change it. All the red boxes are binary blobs. The green things, green is good, are open source. All those red things work hard and take many minutes to finally get Grub ready to load Linux. So Grub is the thing in the transient system load box, and Linux is the thing we actually run. We call Linux the runtime kernel. First step we ever do, and this is what it looks like on systems we're deploying into Google data centers today, as Facebook is deploying on switches and IT Renew is deploying on systems they sell. We remove as many things as we possibly can. Typical example, on a system with over 400 drivers, I've been able to easily remove over 200 drivers and the system still works fine. So we remove as many of the drivers as we can. And as you can see from the upper right where we started, we've removed a lot of other things too. We put Linux in Flash, so it's no longer that transient because it's in Flash. And the Linux has attached to it many programs written in Go, and those programs allow us to net boot or local boot. And depending on the situation, you can greatly increase the security of that boot with signature, disk unlock, and that sort of thing. And we do provide a disk unlock program now in uroot. So step one is remove. Step two is replace. So if you notice, some of those red blobs have now been replaced with the Linux kernel. So we still have the stuff in the lower left. It's about 10% typically of the size of the firmware image. That we can't change on x86. That we might be able to change on ARM. We're working on that. That now goes directly to a Linux kernel, not to the UEFI dispatcher. Drivers that we can't put into Linux, and we hope there won't be any, but there might be some, are now replaced with open source. And we're still running the Go programs known as uroot to net boot or local boot. And that in turn heads out to the runtime kernel. So the steps are remove, replace, repeat. Now I'm going to talk for a minute about how that connects to the open system firmware effort going on at Open Compute Platform. That's an effort I helped start and I co-led for 2 years. It's now led by Ryan O'Leary and at Google and Reddy from Intel. So the goal of open system firmware is that the user control the firmware on the system. So this is not requiring open source. It requires a system that users can own and control. We would prefer that it be full open source, as in the IBM Power, or as in the x86 in 1999 or so, but we recognize the realities of the now closed x86 world. A lot's changed in 20 years. And ARM is a lot further along in terms of full open source, but we also realize that in the ARM ecosystem, there may be binary blobs to this day. So the requirements of open system firmware boil down to users own the firmware, users can create images, users can make those images available outside their corporation. If the images need signing, users can sign them. If the hardware has keys, users have to be able to own the keys, not the manufacturers. So we actually did talk recently to one ARM system vendor who thought the model was going to be that a user would create an image and send it back to a manufacturer for signing and then receive that image back. That's not how it's got to work. The way it has to work is the user has to be able to sign their image inside the organization and then burn that image. And finally, when there are keys, users have to be able to revoke the keys. And we're requiring a minimum of 8 keys. We would prefer infinity keys, as in Chromebooks. And we hope long-term to actually increase that requirement from 8 to a larger number. But in discussions with all the various chipset vendors, we ended up feeling that for now, 8 keys was about the right number. So now I'm going to talk for a minute about LinuxBoot on ARM. So LinuxBoot on ARM uses the uroot userland. Uroot, as mentioned before, is a set of Unix commands written in Go. This is actually a little picture of a small box with a QB truck board. That runs uroot. We actually load the uroot as firmware on this. The box is a lot of fun because I have a USB stick and the only connection outside is USB-C. It's very handy to carry around on airplanes when you can power a whole computer like this from your USB-C port. Uroot has about 145 commands. Over time, historically, we've added a new command about every 3 weeks. We have a way of compiling any Go program, not just a uroot program, but any Go program into a uroot image in a way that we do a source-to-source transformation and compile it all into one binary. That ends up with about 90K per command when we compile it into this single binary in a compressed CPIO. And in fact, that easily fits into almost any ARM system. If you know about the QB truck, you know that's a pretty low power, low throughput system. It easily works on the QB truck. So we've used this on ARM with U-boot, Core boot, and EDK2. Our latest port is to the Ampere Jade Mountain. This is a server class chipset. You can build the image yourself. Thank you to Ampere for doing all the work they've done to make this work as well as it has. And now I will hand off to Francois, who will talk more about this effort.
Thank you, Ron. So, as you said earlier, we can start with minimal EDK2 where you can intertwine LinuxBoot and EDK2 to actually add LinuxBoot in between. Or we can really try to replace entirely the firmware with LinuxBoot. There will still be a little bit of still an open source firmware called Trusted Firmware A that will be there and really do what's called the PI on the x86 and do a very low level initialization of the RAM controller. So both sides are possible, and I would say it depends on what's your platform and what's your objective. If you use EDK2, you may have less effort to actually introduce LinuxBoot on the platform. And it's very easy from an ACPI point of view because everything is already ready with some aspects of EDK2. As you said, there are some aspects of security that may still be a problem, and that, let's say, make the attack surface a little bit bigger. You can replace entirely the EDK2 with Linux, but then you need to actually change or prepare Trusted Firmware A to load Linux. That needs a little bit of knowledge on the platform and on how you deal with those low-level firmware interfaces. So I would say it's easier to be done by the platform owner rather than by the end user, up until the Trusted Firmware A, which is also, again, open source, is fully equipped with LinuxBoot support. In that case, the user will be able to do what you say, Ron, which is owning the platform, changing the keys, assigning the images. So at this stage, we are not yet there, but I think this is going to be very soon available. If we want to have a more in-depth discussion of what it means to actually have the LinuxBoot working, we have to consider two aspects. One is if the platform is an ACPI described hardware, or if it's a device tree described hardware. If it's ACPI, for the moment, as I said earlier, the easiest way is to still intertwine EDK2 and leverage the ACPI implementation there. If it's a device tree platform, then you can just, let's say, tweak around the TFA and make sure that the platform can have the proper device tree for LinuxBoot. In the long run, there will be additional efforts to be done, like supporting what's called a supplicant for RPMB, which is the secure partitions on the eMMCs. So this is a special communication or special agent that will allow Opti to actually leverage that hardware. Opti being the trusted OS that reside in the secure world. Another aspect is what's the contract between LinuxBoot and the booted payload within the runtime kernel, as you called it earlier, Ron. Today, this is following a simple interface, but we can envision to implement a very, I would say, limited version of the UFI interface, so that from a distro perspective, it is very simple and quite the same environment as always, and and make life easier for distro vendors. If that UEFI interface is simple, we can still have secure boot and runtime services. It will be a choice of implementation. We have not yet fully implemented that as a part of the experiments, but it's a promising project. To share a little bit more with what we did as experiments, we made sure that the LinuxBoot was actually 2.1 megabytes as a compressed entity. It was fitting in a hardware partition of an eMMC that was 4 meg big. And then we had the uroot was actually on a different partition so that we can leverage the AB partition, hardware supported AB partitioning of eMMCs. We bumped into a number of issues where actually Linux drivers may assume that some hardware is initialized before them. We bumped into that for SD card, for example. If you boot on an SD card, maybe the eMMC is not available. So there are some tweaks here to be done. But the big benefit of putting LinuxBoot here is that when you use LinuxBoot, you have the full power of multi-core interrupts and the full eMMC performance. So depending on the hardware, it may go up to 10 times faster than a typical U-boot or EDK2 eMMC reading performance. So in that case, the total boot time is significantly lower when using LinuxBoot. So I think that's what I could share in a few minutes about what we did. And now I would like to hand over to Dong to describe more what's going to happen on the ARM ecosystem.
Yeah, thanks, Francois. I'm going to be talking about the relationship between LinuxBoot and ARM System Ready program. So ARM System Ready is going to be a program that I will introduce tomorrow in the session about making ARM devices just work. So now you know that what LinuxBoot is and how it is integrated with the PI phases, how the LinuxBoot relates to the Open Compute project, and how we might implement LinuxBoot on ARM systems. And Ron gave a very appealing example on the Ampere box. So let's talk about what ARM is doing to support LinuxBoot in the standards-based approach. So in the ARM System Ready program that we designed, we want to see software just work on ARM-based devices. So we are extending from the original ARM Server Ready program and to the embedded servers and IoT devices in the edge and IoT space, the purpose of which is to land common OSs on many different hardware produced by the silicon vendors and OEM ODMs. And in the ARM System Ready program, it is one program that will support multiple bands, depending on the operating system and the market segment that your devices are produced for. We have currently developed 4 major brands, and one of which is the LinuxBoot Server Ready. So basically, if you design your system to have your hardware complying to what's called the base system architecture and the server based system architecture supplement, and then you put LinuxBoot as the firmware solution on those server systems, then we do have the System Ready LinuxBoot Ready band to support you. So for the rest of the bands, you can attend my other session to know a lot more details about. But for now, for this session, I'm going to be focusing on the LinuxBoot, the System Ready LS band. So we're focusing on the LinuxBoot RTOS band, right? So in this particular band, I think we leveraged the effort that we have done in the past couple of years on server-ready program, and the same hardware that you design to support these other operating systems for the server-ready. If you put LinuxBoot as the option for firmware, we can certify your system, to be system-ready, supporting the LinuxBoot and the operating systems that LinuxBoot supports. And so in summary, so what we have talked about today is we have described what LinuxBoot is and why we want to do the LinuxBoot on many of these systems, and how it is related to the OCP, the Open Compute project. It has the open system firmware stream inside, or project inside that program. And then we also talked about how LinuxBoot can be implemented on ARM systems. We have real examples for that. And then we also have now the ARM system-ready RTOS band that can support LinuxBoot on ARM servers. So there are related sessions in this DevSummit that you may find interesting in. So there are many keynotes that our executives are going to be talking about many aspects, and system-ready will be one of them. And system-ready sessions, and we also have a panel that will happen tomorrow. And system-ready is also part of ARM's Project Cassini, so you can take a look at what that project is about. System-ready fulfills the standards pillar for the Project Cassini, which also covers security and cloud-native applications. And we also have, pre-silicon certification program for people who are designing the hardware for these operating systems and software to run. And many times we find issues in the compliance to the hardware standards, and the pre-silicon will help people on that. And this LinuxBoot on ARM is one session in this scheme. So we have this session today. And of course, you can also take a look at some of the other sessions that are related to the hardware and software technologies that ARM is here to support. So with that, thanks to Ron and Francois to provide us with a lot of these materials. And thank you all for attending this session, and enjoy the DevSummit show.